I'm still running my life, so.
Yeah.
Hey, how y'all doing?
Pretty good.
I am so glad you unmuted to say that because I always have that self-doubt thing going on and like, have I unmuted and did I set the volume such that I can hear you? So yeah, we're all good. Or at least two of us are good. Uh, Zoom is great in some ways. Here's how it's really good and really bad at the same time. Zoom allows me to, well, I haven't had to leave the house yet today. And so that's really cool in some ways. But right before class, I thought, oh, hold on. I'm still wearing the same shirt that I was yesterday at class time. And boy, that would be embarrassing to wear the same shirt 2 days in a row. So I had to run and change really quick. And so I guess that's a good and a bad that I don't have to sort of like stress over leaving, but the self-imposed like, oh my gosh, that would be embarrassing thing. So good and bad both. Hopefully you guys are doing really well. Where I know we're at is there's this test coming up tomorrow. We didn't have any questions yesterday in class on the homework problems assigned Monday and Tuesday and due yesterday. I have yet to put the answers online for that. I should be doing that shortly. And so you'll be able to review those answers before we move forward and take the test. But if you're ready, the test will be live as of 1 o'clock. But you as a group may have questions related to either homework problems assigned recently or the sample exam. So maybe what we should do is let you guys ask administrative questions and then subject matter questions that tie to specifically what will be on your test, or what I should say, think is likely to be on your test based on what we've covered and the sample exam. So any administrative questions first? While you're thinking of an administrative question, let me just say it's sort of like that first exam, other than I think I set it up so that way about half the points are more auto-graded. Some of them are, some of the questions are auto-graded, like it's like a number, you type in the number. Or perhaps it's multiple choice. You can get 4 choices. You pick the one that you think is right, and so that's one of the things you'll have to do. And some of them are more free form, and I try to set up so that we could probably type an answer in if you would find that more convenient. Sometimes, however, like with the first test, to type in your answer, you would want to do some calculations or scratch work. Okay, just please label that with the problem number, and then, like last exam, scan it and upload. And again, it's a 50-minute test, but that gives you about 5 minutes to then scan, create a PDF, and then upload any scratch work you'd like me to look at. So question, Muska asks, sections 5.4 through 5.6 on the exam? Yeah, they're on the exam. And so that's content on sampling distributions. So literally, if I were to random variables 5.4, but 5.5 and 5.6 are on sampling distributions, where if I were to sample from a population, could you tell me about the possible sample averages? That's sort of the big topic in 5.5 and 5.6. Other possible topics is sort of like this. Well, what if I were to sample from a population and want to know about the distribution of the possible sample standard deviations? There's a distribution of the possible S values, okay, that I could observe. And you can find actually, and this is sort of something that tied to our earlier lab, not from yesterday, but way early in the term. If I were to sample and define my standard deviation with an N instead of an N minus 1 in the denominator, and that's where talk about a variance, we would have a biased estimate of the variance, okay? And that's a problem. A biased estimate of the variance is a problem. You have to divide through by N minus 1 to get an unbiased variance estimate, okay? And so that ties sort of nicely with both recent chapters that we've looked at. So yeah, a lot of good content there in sampling distributions. Sort of wraps up a lot of what we've done with probability and some of the earlier content. So Julian asks, can you leave all the answers on a PDF piece of paper? And the answer is, oh yeah, you can. I think if it's a numeric answer, I would appreciate you just typing the answer in. But if it's like one of those essays, if you don't want to just type everything out, that's fine. But again, the numeric only answers, just take the time to type in 1.532 or whatever, okay? Okay, so homework 3A, problem 14. Let's look at that one. I have to find homework 3A. And which, was that out of chapter 5 or chapter 5, right? 5.3, good. I'm right there, and I'm going to drag our book over, and we could talk about that just a little bit. Okay, so good. And let's make this bigger so we can read it more easily. So there's a tree diagram that we're supposed to refer to, and if you want to find the probability of B given A, you could write it out. Okay, so this is sort of like using Bayes' rule. In fact, it walks you through Bayes' rule, and so or Bayes' theorem, I guess, is what it's called in 14 part C. Okay, so yeah, we did something a lot like this in class example. And so 5.7, I don't know if I can find that easily. Let's see if I can go up and find that. If you could tell me the page on which 5.7 figure is, that'll be quicker for me. Figure 5.7. That's not it. Okay, but it's the previous figure. Okay, there we go. B, B prime, A given B. Okay, so there we go. Okay, so I now remember what that figure is. And let's look at problem 14. Okay. Use the addition law to show that P of A is P of A and B plus P of A and not B. So let's maybe move over here to the left. Let's move this over here to the left in a way where I can still see that. Okay, and make this smaller. And so I remember approximately the diagram. So it's and let's go with pink. Okay, so there's either B or B prime. And then there's A, well, probability of B is what's showed there. And A or A prime, A prime. Probability of A given B is shown. The probability of A prime given B. Okay. And then our friends A and A prime again. Probability of A given B prime. And probability of A prime given B prime. Okay, so part A here, lowercase a, asks us use the addition law to show that A and B is probability of A and B plus the A and B prime. Well, that's sort of the definition of the addition law in this context. We've got these two disjoint events, okay? And the two disjoint events are like, well, everything that's in A but also B, intersected, not intersected, union with A, everything that's A that's not in B. So if I were showing this in terms of the figure, I've got everything that's in A and B. So that's the first part, okay? A and B. A and B prime is right over here, A and not in B. And the probability then of these two events, the probability of A has to be the probability of the two disjoint events that form it. Okay, so that's A and B plus probability of A and B prime. So I sort of showed it graphically, and you're saying, okay, yeah, that works. Okay, use this conditional probability formula to write out probability of A and B in terms of okay, so the conditional probability formula, we would phrase it the following way. Probability of A given B, okay, is equal to the probability of A and B over the probability of B. Or if I do algebra, okay, just like move the denominator over to the left-hand side, the probability of B times the probability of A given B is the probability of A and B both. Okay, so that's part B. Check. Any questions about A or B so far? Okay, so I guess if I were to do the same sort of thing as I did for A and B, being A given B, well, okay, so I did only half of this problem. Okay, so I did this part to right there. I did the first bit, but the second bit is the exact same. I guess if I go through and put a prime on top of every B, we will have completed the second part of problem C. Okay, check. Okay, so if I were to go up top and I'm going to remove the figure. We could always refer back to it if you'd like to, because it's in the book just a couple pages back. I now can go ahead and use the definition here of B given A, okay, and then do a little bit of work. So probability of B given A, okay, is equal to, here's by definition, probability of A and B both over the probability of A. Conditional probability definition. And so doing the work that we have just done earlier, I could write the numerator as probability of B times then the probability of A given B, okay? And in the denominator, I've got my earlier work from the first part of the problem. I could write that as probability of A and B plus the probability of A and B prime. And in part C, I'm sorry, part B, we could sub in for each of these two terms in the denominator like we had done in the numerator. So we've got probability of B times the probability of A given B over then that same thing, probability of B times the probability of A given B plus the probability of uh, B prime times then the probability of A given B prime. Okay, so here is our way of writing Bayes' theorem or Bayes' rule. Check. Okay, so y in figure 5.7, here's question D. Y in figure 5.7 is the probability associated with any path, simply the product, okay? I guess I could multiply together those probabilities. Well, I think we could get after that by, and I apologize for, let's just clear the whole thing and go up a couple pages to look at the diagram again. Okay, there we go. Yeah, literally A and B, okay, is the chance of B happening times the chance that A happens given B has happened. So here we would multiply as we head to the right, our main branch times then the probability of going down the second branch given you went down the first branch, okay? Or in any of these four situations. And this is with just four situations. You could have it, with more than four situations. Your first branching could correspond to I roll a die and I have either one, a two, a three, a four, a five, or six. And then the second set of branches could correspond to the number of times we roll the die again is the number according to that first branch. Yeah. And so we could have six branches and then hanging off the first branch is just one branch. Hanging off the second branch is two. Hanging off the third is three. Following branches off the fourth branch, we get four follow-ups. There's a lot of possible ways of setting up one of these tree diagrams, but in all cases, on the diagonal is where we have either the main probability if it's our initial branch or a conditional probability if we've gone down that branch a little bit more, okay, a little bit further. Let's look at part last of this one, and then I want to mention one other thing about, so use the observations for part D and the conditional theorem to justify Bayes. Okay, so yeah, I don't know how I would tackle part E. I'm saying, well, it's just using these probability rules, the if you will, the sum of A, lowercase a, B, C, and D is the statement E. So we've just done that proof. The collection of these guys gives us that, in my opinion. Okay. One thing I probably could have followed up on in our Bayes rule section was when we were talking about the UPS drivers. Some are using drugs, others have not been, and then either they test positive or they test negative, positive and negative. What I thought was ultimately there's a relatively high chance that the person who tests positive for drugs actually hasn't been using. Okay, so let's put the numbers here. We get 0.05, 0.95, 0.95 is the chance of going down that diagonal. And testing, there we go. Darn it, let's go there. Okay, so I'm messing up my diagram. Okay, so now I could draw again. There we go. And then if I were to be actually using, the chance that I test positive is 0.98, 0.02. It's a chance that I falsely test negative. 0.01 of the people will test positive if they haven't been using, and 0.99 will test negative if they haven't been using. And we ultimately discovered that the probability of actually using drugs, given that they tested positive, or better yet, the probability that they're not using drugs, given that they test positive, is too high for me to feel comfortable. Okay. We could change our process a little bit and say everyone who tests positive, we will retest them. Wait a week and do a retest. So we're going to get another branch down here, positive twice in a row, or positive followed up by a negative. Same thing here. And those that weren't using, they might test positive twice in a row, or they might test negative. But only 1% of those who literally tested positive the first time incorrectly will test positive incorrectly the second time. And so we're going to end up with only 1 out of every 10,000 non-users will ultimately be testing positive. And the bulk of those that test positive twice in a row will be in that using community. Okay, so always ask for a retest. And this is why sometimes, well, y'all remember Shaun White, who was in the Olympics, who tested positive for marijuana and lost his gold medal in snowboarding? I always thought it was only performance enhancing drugs that we should be worried about in that context. But yeah, ask for the retest. Okay. So clear that off. One thing that I also, in reflection, didn't think we emphasized enough, and that is the concept of independence. Probability of A given B, it's equal to the probability of A and B over the chance of B. Sometimes that's literally equal to the probability of the event A happening. In other words, whether B has happened or not has no impact on how likely A is to happen. If probability of A equals probability of A given B, it would also equal the probability of A given B prime. Okay. And we would say, if that's true, we would refer to A and B are as independent events. And if you have independent events, the cool thing is our probability, our multiplication rule in general, which was probability of A and B, could be written as the chance of B times the chance of A given B. Okay. I would have the ability to say, well, if we have independent events, this is just probability B times the chance of A. So independent events, it simplifies that probability rule. And that could be a helpful thing and useful. So if the problem says A and B are independent events, you got the ability to use that shortcut. Okay. So I want to be sure to mention that before we move further forward. Okay. Any other questions? Because that was like one question plus me feeling the need to ramble on about related issues that I think would be helpful, but maybe we should have you lead the discussion by your choice of questions. Okay, 23 from section 5.3. So if I could find that, I will, yeah, let's look at it. And where did I? Over here, and maybe clearing that. Let's look at problem 23. So down a little bit. Okay, so okay, so 1% of individuals are carriers for a particular strange disease. Diagnostic test, 90% detection rate for the carriers. And if you're a non-carrier, it will falsely say that you have the disease 5% of the time. And suppose that diagnostic test applied independently to 2 different samples from the same randomly sampled person. What's the chance that both yield the same result? So we sort of tackled problem B already. So I'm going to focus on part A oh, I'm sorry, problem 23. Yeah, okay, good. So let's look at problem A at first. Okay. And so maybe again, moving this over here off to the side, I can then look and do a little bit of work and get an answer that makes me happy. Okay, so clear that and move forward. Okay, so 1% of people carry a particular disease. So I'll say D for disease, D prime for not disease, 0.01, 0.99. And then if you do have the disease, you're going to 90% of the time, you're going to test positive. And if you don't if you have, excuse me, have the disease, you'll test negative 10% of the time. But we're going to do a second test for each of these individuals, plus and minus. And of those that don't, again, 0.9, 0.1, 0.9, 0.1. Of those that don't have the disease, 5% of the time, 0.05, they'll test positive, and 0.95, they'll test negative. And again, there's another branch, plus and minus, 0.05, 0.95, 0.05. I'm sorry. Let's go back a little bit. And I'm going to have positive and minus 0.05 and 0.95. Okay. And so I'm going to just sort of try and highlight the condition that part A asks about. Both tests yielding the same result. So they yielded positive followed by positive. We're down here. That would correspond to both the same. Negative, negative, positive, positive, negative, negative. So these are the four conditions that should be getting the exact same result. And the chance of being in that first slot is 0.01 times 0.9 squared. This second slot is 0.01 times 0.1 squared. This third slot, it's 0.99 times 0.05 squared. And that fourth slot is 0.99 times 0.95 squared. And so I'm looking at these numbers and I see something like small and small, well, big and small, small and big, big and big. So almost certainly it's like the bulk of it's right here. Okay. So you could find those chances in part A. What about both tests being positive? What's the chance that the person actually is a carrier? Part B is like we suggested earlier. Let's do a small bit of erasing and then get after that. And I'm going to leave only the portions where we test positive twice in a row. And that would correspond to, well, just those two remaining purple circles. Okay. And there's only two ways of getting down there at that final end. That's the denominator chance in that conditional probability, the probability of having the disease given that you test positive 2 times. So given positive, positive. Okay. So if you test positive 2 times in a row, what's the chance that you actually have the disease? And that looks like an H, but I really meant to be positive twice in a row. That would be positive twice in a row, and that's 0.01 times 0.9 squared plus 0.99 times 0.05 squared. Okay. And then actually having the disease and testing positive twice in a row is just the 0.01 times 0.99 squared. Okay, so I think we got that one done. Do any of you want to, and in particular, Anna or Anna, want to follow up on that? Any of you? Okay, I'm reading that as a no, you didn't. So problem 21 from section 5.3. So let's go up a little bit. See if we can find problem 21. Okay, I like this problem in some ways. And so I'm going to just try to sketch this out over here at the right, and then we'll go. Actually, I'm going to try and bring it up to the very top, and I'll just trace over the top, and then I'll move the whole thing to another location. going to sketch over it with red. And I don't know if I didn't read it correctly, but I'm thinking, oh yeah, like those fun diagrams, like with those 3D pictures with the blue and the red. Yeah, and that worked out nicely. Okay, so let's move this over here to the side and go down. And so if we can read the problem then. Okay, so components 1 and 2 are in parallel. So if either pump 1 or 2 works, then the you can go down that path. But you've got this series 3 and 4, and that will only work if both of them are working, and any given component has a 90% chance of working. So 1, 2, 3, and 4. So the probability of the system working is it could be written as the probability that 1 works. Oh, let me just rewrite this. Probability of 1 working, or probability that 2 works, or 3 and 4 both work. Okay, so it's a union of those 3 situations. Okay, and they're independent of each other. So whether, and this is maybe not realistic, but we're going to assume they're independent of each other and they all have a 90% chance of working. And so let's maybe tackle one sub problem first. What's the probability of 3 and 4 both working? Probability of 3 and 4 both working. Okay, that could be written as a probability of 0.9. Let's write that more clearly because that writing was bad. 0.9 times 0.9. So the chance that they both work, 0.9 squared. Okay. So what about the probability that 1 or 2 works? Okay. And sort of the upper pathway that we could be taking. I'm thinking, pumping water uphill in California or something like that. So that's 1 minus the chance that neither work. So that's 1 minus 0.9 squared. So they both have to fail. So neither 1 nor 2 would be working. So the 1 or 2 working is 1 minus 0.9 squared. And I don't know what that is. Well, 0.9, 1.01. That's 0.99 here. We got 0.81. So I think I got those numbers correct. Okay. So what about track 1? I'll call this T1, and this is T2. And it's really track 1 or track 2 working. What's the probability of T1 or T2? Okay. And that's 1 minus the probability that neither work, so T1 prime, and T2 prime, that both subsystems fail, that no one's working. Okay. So I guess I could, because we have independence, I could write this as 1 minus the chance that the first system fails. That's 1 minus the chance that it's working. So 1 minus 0.81 times then 1 minus 0.99, 1 minus 0.99. Okay. And I'm sorry, no, 1 minus 0.9 squared, so that's 0.01. Yeah, perfect. So what do we have here? Well, 1 minus 0.99 is only tiny. 1 minus 0.19, move that over 2 slots, 0.0019. 1 minus 0.0019, or if you will, 98.9881, something like that. I might have mathed incorrectly, but I logicked, I believe, correctly. So Edison, you asked about that. Is that something you said, okay, I track with that, I'm happy? Well, posterity may have the video being upon rewatching, everyone says, okay, yeah, yeah. Anyone want to do a follow-up?
I just had a quick question. Why is it
Sure.
the probability of T1 or T2 and not T1 and T2?
Yeah, great question. Okay, so in the California aqueduct, and I sort of drive every so often up to Sacramento, there's this one section where along, at least the way I choose to drive, you see this huge pump going uphill, like a tube and a pump at the bottom. But then you realize, like T2, there's another pump further up the hill. So it like goes up and then level for a while, then goes up again. But there are other stretches along that drive where you see like track one, okay, where if either of these two things that's pumping up water hill, if either of those two are working, we'll get water up the hill. Okay. Track one is actually one of the two paths that if either of the two paths work, then the system as a whole will work. Basically, I'm sort of considering water and the ways that the water could get from off to the left to the right, and it could take path pump one only, and that's fine. If it goes through pump one, we're all good. It gets uphill. Or maybe it goes through pump two and gets uphill. Or if it takes this alternate path and goes through pump three, it has to also go through pump four and uphill. And so like track one and track two is sort of like just track one, but replicated again. So either of those 1, 2, 3 ways of getting uphill, it could work. So you could either take track one successfully, or track two successfully, or track three and four. So or, and then or. 3 separate ways of getting there. Yeah, so that's a great question. And I'm glad you asked that because it allows me the opportunity to say on a test, like, the one that you'll look at later today or perhaps tomorrow, the reading sort of matters. And if you look at the picture and then read it and you hear it as and instead of the or, you're going to be using a different rule, and I will spot that as mathematically incorrect. The answer you will get is not the same as the right answer. But usually when you write it down, I can say, oh, that person had this mental error and they used an and instead of the or in this problem. And conceptually, that was an oversight or a minor error compared to being unable to do this part or that part separately. Yeah. And so if you do parts of it completely correctly, but you put it together wrong, like Lego sets and the really big ones these days, I am always the guy who like skips that one step on page 3, and I find out on page 20 that oops, I have to go back and rebuild a bunch of things. Okay, take it apart and rebuild it, and that's okay. Okay, I can say, looking at your exam, oh yeah, you did the step wrong on page 3, but the rest of the things you did were all reasonable considering what you did in error earlier. The only situation where I won't try, I'll try to, the only situation where I don't feel completely comfortable giving you full credit for using an earlier answer in error, like you made a mistake on part 3 and then you use it on part 5. I'm usually going to give you full credit for doing part 3 correctly and when I'm grading part 5. The only situations where I can't in good faith do that is if where because of that mental error, on part 3, you get some error that's like a nonsense answer later on part 5. If literally you should say, hey, that can't be right. If you say to yourself, there's no way, or if you should say to yourself, there's no way that that answer can be correct, like a probability of 150%, that's not going to happen. So if you should spot things and don't spot them and then go back and, maybe fix the earlier thing, it makes it a little bit tougher to use your errant inputs to give you full credit for later. Okay. So I'm glad you raised the issue, Anna. Anyone want to follow up on any aspects of this problem? Okay. Do any of you have questions from the sample exam? Which I think I'm finding. Okay. Use my thumb and go to there. Okay, it's over here. Good. Any questions from the sample exam? I would like to believe, and from past students, they've told me that, having two sets of answers is really helpful, but that's assuming you read them and have looked over the sample exam. And I don't know whether you have, but on the earlier exam anyway, did y'all find that the answers I provided on the sample exam tended to be sufficient and helpful?
Yes.
Yay, I win. Okay, so how about then this sample exam? I'm happy to walk through it and comment on things I notice in the exam as an instructor from the point of view of someone who is an instructor who writes exams. What are the sort of things that might have caused that instructor, me, to have put that question? Like, what am I aiming for? Would you like me to walk through the exam and sort of comment on those things?
Yeah, I think that would be good.
Okay, so let's do it. So on this sample exam here, so I'm going to try and comment on why would I even ask that? And here are the sorts of things which, if a student had seen it, it would make it easy for them or easier for them to solve the problem. Okay. So I'm noticing here right up front, yeah, I'm just telling you about this probability distribution. It happens to be called the negative binomial probability distribution. If you remember reading through that, here's an example of that. But basically, I'm going to roll a die until I get a 1 or a 6. That's going to happen like a third of the time on any given roll. So the first roll, that happening would happen with chance 1 and 3. However, the chance that happens on that second roll, okay, or the third or fourth, we could calculate, and I've just put in some numbers here for you. The fact that I didn't continue means either the probability distribution in general should be sufficient, or all you're going to need is mu and sigma squared. Okay. And yeah, literally, I will sometimes give you information in how the problem was created, but not all of it will be utilized. Okay. So here, probably it's going to be the bulk of it, information is going to be found right there. Okay. Why is X random? My answer is, well, yeah, because I don't know what X is going to be before I do it. The answer is numeric but uncertain definition of a random variable. So are you going to roll a die in 1 or 6? What's the chance that it takes you 3 or fewer rolls? Well, probability rules, I could add up the chance of 3 or fewer, no problem. To A and B, okay, so yeah, I'm thinking A and B here. And the results are independent of each other. And that makes sense because they're rolling dice. Mutual exclusive versus independent. Why would I even ask about that? Okay. So yeah, literally, if Allie gets a 1, does that mean Beatrice can't get a 1? Mutually exclusive? No. They could both get the same result. Why would I ask about that? Students will sometimes hear independent as, oh, this is not related to that. And mutually exclusive, they'll sometimes think this is not related to that. Using sort of a not clear definition of either independence or mutual exclusivity or disjointness, you could end up thinking that the two terms mean the same thing when they don't. Okay, chance that both of them have 3 or fewer rolls. Well, that would be A is 3 or less and B is 3 or less. I guess I could use the multiplication rule and independence and just multiply the chance of 3 or less, which we found earlier by itself. Okay. What's the chance that at least one of them? At least one of them. Okay, when you hear things like at least one, you should think a logical opposite. Oh, 1 minus the chance that none of them have 3 or fewer rolls. Okay, so both of them and neither of them. So maybe numbers that you're going to see, here, like in part B, okay, will be playing a different role. If you find both and at least one, yeah, the solution would be really different in the way it looks. Okay. So what if I tell you that at least one of them does have 3 or fewer rolls? What's the chance that both of them Well, your answers in D and E might be super helpful because you know the conditional probability of both, given that at least one has 3 or fewer rolls, is the intersection over the chance of at least one having 3 or fewer rolls. So it's just the answer in D over the answer in E. So notice that I'm setting you up in earlier problems to be able to quickly plug numbers in on later problems. Okay. Okay, now we get into where the average, mean, mu, 3, and the standard deviation, the root of 6, would be used. Okay, so what's could I find for averages? Could I find what's going on? And I guess I could list off a lot of ways of getting an average of 2.5 or less. I guess they both have ones. They both have one's a 1, one's a 2, or one's a 1 and one's a 3. Or one's a 1 and one's a 4. That also counts. So I guess I could list off those possible ways of doing it. And that's going to be something like A1, B1, A1, B2, A1, B3, A1, B4, because that would all correspond to the sum being 5 or less. A2, B1, A2, B2, A2, B3. And if I go to A2, B4, the sum would be 6. So the average would be certainly more than 2.5. A3, B1, A3, B2. And then I have to stop. And A4, B1. So these are the only ways of getting the average being 2.5 or less. Okay. So 2.5 or less, that's problem 2B. Okay, so could I find the chance? Well, I guess I could find the chance of all of those and add those up. Okay, so I could find the chance that the average is 2.5 or less. Now, why would I ask this question, part C here? You just listed off every possible way of the average being 2.5 or less. We all sort of agreed, no, I agreed in my own mind with what I think you were thinking, that part B is, that was not hard. Listing off all of those possible ways was doable. And there's only 10 of these possible ways of doing it. And shoot, we even could find the chances pretty quickly because I know stuff from above. So in part C, why would I ask you this? Well, earlier in class, we did tell you that if you have the mean and the standard deviation both known from a population, you can find the chance that the average is in a certain value by using the normal curve if the population is normal and this population of possible values is not normal, or if you have a large sample size and a sample size of 2 is not large. And so many students would be tempted to answer, oh, no, you can't do it. Right after telling me every one of the possible ways of having the average being 2.5 or less. So yeah, literally we have to find 10 separate chances and add up those 10. You can do it, but many students, because they had only recently learned normal curve as a way to find what's the chance the sample average, yeah, they incorrectly said, oh, no, normal is the only approach I could take. No, you could take the direct approach. And with a sample of size 2, a direct approach is often very solvable. If you get, however, to 6 individuals, like we do move on into in part C, it becomes a lot harder. Okay. So on question 3, so 3.5 is the average, less than 3.5. 6 people are going to play the game. I guess it's possible, but notice it says using the methods we've studied so far. Okay, I guess I could write out a summation with 6 terms in it, summing over like I, J, K, L, M, and N as indices of summation. But that would not be what I would expect you to do, okay? One student came up to me during the test when this question was asked and said, do you want me to really write this out this way? And I said, well, you've already started writing out this way, and your answer is completely understandable. And the guy finished, took another minute and got it right. But most of the students said, nah, no, too complex. And the reason is n is not big enough to use the central limit theorem, not big enough to know the distribution of the possible sample means is following a normal curve. But if n is 96, we're okay. So either a normal population or a large n will allow us to use the normal curve. Okay. So I love question C, and question C is, even though you couldn't do it there, but you could do it in part B, which chance is larger? Or can you not determine? Okay. That's a tough one. Let's consider a smaller case, maybe. Instead of 6 and 96, what if it's like 2 and then the average of 2? Okay. Or no, hold on. No, I'm sorry. I was misspeaking. I was thinking about a different question. Okay, so one of the things we find in our rules from yesterday is sigma sub x bar, the difference between a sample mean and then the average of the population, mu, is sigma over the root of n. And so in the case of 6, sigma over the root of 6 versus the case of 96 is going to be sigma over the root of 96. Which one is a smaller number? Well, sigma over the root of 96 is smaller. And so, if you will, the distribution of the possible sample means is going to, for a sample of 96, be much tighter around that mean mu. So the chance of 3.5 or higher is going to be sizable versus like negligible. Let me rephrase that. The larger the sample size is, the closer the sample mean is to the population mean. Let me flip that on its head, though. The larger the sample size is, the less likely the sample mean is to be unusually large. Larger sample, closer to the population mean, therefore less likely to be in that unusually large range, like 3.5 or larger. Okay, let me try and focus in the last minute on this last question. This last question is, if I tell you about within a row, here are conditional probabilities. Probability of D given low, the probability of I given low, and the probability of R given low in that first row, and then probability of D given high, probability of I given high, and then probability of R given high. Okay, you could even write this out in a tree. There's the low and the high, and then we have the separate probabilities of D, I, and R. Okay, so we've got a table here, and these are conditional probabilities that are given to you. Conditional probabilities should make you think sometimes a tree diagram will be helpful. If you're given conditional probabilities, tree diagrams. Okay. So it looks like it's going to be a Bayes rule problem because we have D given L and then L given D both found in the problem. And so you're given one of them, you have to use Bayes' rule to find the other. And we're walking you through the steps to do it. Okay, so part F is the one that I think is allowing me to get insights into the level of statistical input. No, get understanding of your level of statistical thinking so far. And that is, could I answer the question? Is having a low draft number going to change my opinion about politics? Or would having a high draft number change my opinion about politics? Are there any two numbers that I could compare? And there's a couple reasonable answers, but I think comparing those two makes sense, or comparing these two would make sense. Is a person more likely to be a Democrat if they have a low number? Could be rewritten as, are they more likely to be a Republican if they have a high number? And the answer in both cases is yes. Whether you're likely going to be drafted or not to go fight in Vietnam has something to do with whether you approve of the party that pushes for that war. Okay, so couple different reasonable answers. There are again more reasonable answers. When you're comparing two numbers, you could create your own comparison of two numbers. I'm just saying here is one way you could do it, just those two, or just these two. Some students came up with like a different comparison that included both Democrats and Republicans, and more power to them, but they didn't get better credit because they were just as right as those who answered this way. Okay, office hours between now and when the exam is due. Today, later at 5:10. Happy to tackle questions. And also Friday at the Friday afternoon or Friday morning time slot. And that time slot is, I believe, 11:30 approximately till 12:30. Actually, it's like 11:35 to 12:25. And I might need to be real careful about ending right at 12:25 because I have a 12:45 p.m. appointment in San Luis Obispo. And if I'm doing that office hours from home rather than from campus, I might need to leave very promptly. So if I can possibly be on campus, I will do that on Friday, which will give me another 5 minutes worth of office hours. But certainly show up on time, 11:25, if you got a question. Okay, any quick last